All right, we're going to look at some other types of units that we can use to define the concentration of a solution. So we spent a little bit of time on molarity, which relates the number of moles of a solute to the whole liter of solution. And so what we're going to look at are some alternative concentration methods that relate different aspects of the solute to the solvent. So another way of reporting concentration is to use mass percent. And in mass percent, we're going to relate the mass of the solute to the mass of the solvent. I'm sorry, the solution. And then we multiply by 100 to put it into a percent. Now, I do, again, want to highlight when we talk about solution, that is solvent plus the solute. Sometimes you might see this abbreviated like this, W/W percent or weight by weight percent. Um, And the units of mass don't matter as long as they are the same because they have to be able to cancel out. So you can have them both in grams, you can both have them in kilograms or milligrams, whatever. They just have to be the same. So let's kind of look at an example. So liquid bleach is 7.4% sodium hypochlorite by mass. How many moles of sodium hypochlorite are there in 1 kilogram of bleach? And then the molar mass is there for sodium hypochlorite. Um, Now the question is in these kinds of problems, how do I deal with a mass percent? And there's a very easy way to take that and put it into a conversion factor. Whenever you see these percentages, always make an assumption and make an easy assumption. Let's assume we have 100 grams of this 7.4% solution. Because if we have 100 grams, then the conversion factor we can use is 7.4 grams of sodium hypochlorite are in 100 grams of the solution, or in this case, bleach. I'll use the specific indicator here, bleach. And we can use this as a conversion factor. And you're going to see me do this a whole lot, where we're going to take a percentage, and then I say, assume we have 100 of it, because it's really easy to multiply anything by 100. Or 7.4% of 100 is 7.4. So just kind of make that percentage into a conversion factor. So let's start with what we're given. We're given 1 kilogram of bleach. And we'll want to get down to grams. So that'll be our first conversion here. So kilograms of bleach on the bottom. And then there's 1,000 grams of bleach. Now notice what happens when I've done that. I'm now in units of grams of bleach. And if I just take this conversion factor I made here, I can get to grams of sodium hypochlorite. So I take this conversion factor, and now grams of bleach cancel out, and I'm left with grams of sodium hypochlorite. Now, if that's where if that's what the question asked me for was mass, then I'd stop. But it's asking us for how many moles there are. So in order to go from grams to moles, I need the molar mass. So that's given to me in the problem. As a side note, how would I find that if the problem didn't give it to me? Well, I'd start adding up all the masses from the periodic table. So keep that in the back of your mind. So I will put the 74.4 grams on the bottom and the moles go on top because that's the unit I want to go to. And now all units cancel out. I'm left with moles of sodium hypochlorite. And keeping track of sig figs, I throw that in my calculator. And I come out to 0.99 moles of sodium hypochlorite. Now, again, it's very important that you keep track of the subject of each of the units. That's why I was cautious to, or not cautious, but emphasizing using grams of bleach versus, say, grams of sodium hypochlorite so that I know which mass unit I was talking about. Okay, let's do another example. So what mass of a 4% sodium hydroxide solution by mass contains 15 grams of sodium hydroxide? So again, when I see this 4% stuff or percent mass things, I'm just going to make that a conversion factor. I'm going to say 4 grams of NaOH on top and 100 grams of the solution. So I'm going to start with what I'm given, 15 grams of sodium hydroxide. And notice what the problem is asking me for. The problem is asking me for what is the mass of the solution? Okay, the sodium hydroxide here is the solute. So this is why keeping track of the subject is important. So I want to go away from grams of sodium hydroxide and I want to go to grams of solution. So grams of sodium hydroxide cancel out. I'm left with grams of solution. That's what the problem is asking me for. And so that comes out to 375 grams of solution. All right, let's look at one more. So a throat spray is 1.4% by mass phenol, and there's the molecular formula in water. If the solution has a density of 0.9956 grams per milliliter, calculate the molarity of the solution. All right, so we got a lot going on there, kind of intermixing a lot of different things, but let's just kind of look at what we're supposed to go to, molarity. Okay, let's think about what that means. If our end goal is molarity, what does that mean we have to get to? Well, we have to get to something with moles and something with liters. Okay. Now, with liters, that, is kind of doable because we have something with milliliters there. So we can do an easy conversion to get to that. Now, in order to get to moles, we have to know mass. Okay. Well, we have two things here that relate mass. We got the mass percent and we got density. So we're going to use those things as well. So the very first thing that I want to do is deal with this 1.40%. Okay, so that as a conversion factor, we're going to write out as 1.40 grams of phenol over 100 grams of solution. Okay, and that just so happens that's what we're given. We're given the 1.40%. So let's start there. 1.40 grams of phenol in 100 grams of that solution. Okay. And do I have anything about, if I want to get rid of grams of solution? Because I want to keep the grams of phenol because I got to get to the molarity. So notice here it says the solution has a density of 0.9956 grams. So what that means is I can put that 0.9956 grams because that's the solution in 1 milliliter of the solution. So the grams of solution cancel out. Now, if you notice what I've done here, I've introduced volume. So let's get that into something that will go into molarity. So milliliters will be on top, liters will be on bottom. There's 1,000 milliliters in 1 liter. So those cancel out. And I'll add this subject in here as well. So that'll get me to my volume for molarity. Now, how do I get to moles? Well, I have grams of phenol, and I have the molar mass of phenol right here. And so I just plug in the numbers. 1 mole weighs 94.11 grams. Grams of phenol cancel out. Notice the units that we're left with here. Moles of phenol, that's our solute, over liters of solution. That's all molarity. So I toss this in my calculator, and that comes out to 0.148 molar phenol. Now, if you want to say M, capital M, that's fine. If you want to say moles per liter, that's fine as well. Now, related to this is volume percent. So if you know what mass percent is, everything is in mass of solute over mass of solution. Um, volume percent, or what we say percent volume, or you might see it like this. It's not as commonly used, but I still want you to know it. You might see it pop up every now and then. But the formula is very similar. It's just that everything is in terms of volume. So I have volume of solute over volume of solution times 100%. And we can use those percent volume numbers just like we did percent mass to make conversion factors. So like if we look at this problem here, rubbing alcohol is 70% isopropanol in water. If the density of pure isopropanol, I want you to kind of highlight and star that, is 0.789 grams per milliliter, how many grams of isopropanol are in 585 milliliters of solution? Now, the first thing I'm going to do is take this 70% and make it a conversion factor. Okay, 70 milliliters, and I'm just going to abbreviate this but isopropanol in 100 milliliters of solution. Now I'm given 585 milliliters of solution. So let's start there and use our conversion factor that has milliliters of solution in it so that we can get rid of it. So milliliters of solution can convert into milliliters of isopropanol. And my conversion factor is 70 milliliters of isopropanol or in 100 milliliters of solution. Now, the only other thing I can use right now to relate milliliters to grams is the density. I want to get rid of milliliters of isopropanol and get to grams of isopropanol. So the density is 0.789 grams per 1 milliliter. And notice milliliters of isopropanol cancel out. Now, before I put this in my calculator, I want to highlight something important. You might be looking at this and saying, well, why didn't you just use the volume and use the density? Like, why didn't I do this? I mean, that seems like a much shorter calculation, would have saved time. I didn't even need the 70%. But did I really? Like, I really can't do this here because this unit is not exactly the same as this unit. The density refers to pure isopropanol. The 585 milliliters refers to the whole solution, which is not pure isopropanol. So I can't do that method. And that comes out to 320 grams of isopropanol. Notice the sig figs here, I can only take two. The 70% um, only had two sig figs in it. All right, and the last type of concentration we're going to look at is what we call parts per million and parts per billion. This is usually used for very, very, very small amounts of solute. And often it's kind of used to judge the purity of, say, like water or wastewater or pure, like well water or things like that. So the way we calculate parts per million is to take mass of the solute divided by the mass of the solution times 10 to the sixth. And then parts per billion, it's the same formula. So mass of solute over mass of solution times 10 to the ninth. Now, how the question that you might have is, well, how do I use these as conversion factors? Okay, there's a really easy way to use them as conversion factors, just like we did with percent mass and percent volume. So if we look at this example, if the concentration of lead in water is 15 parts per billion, what is the mass in micrograms of lead in 450 grams of solution? Okay, so how do we make this a conversion factor? Well, we're just going to take that 15, and what that means is that there are 15 grams of lead and 10 to the ninth grams of solution. So that's how we're going to use this. If it had said 15 ppm or parts per million, we would have said 15 grams over 10 to the sixth grams. So let's start with what we're given, 450 grams of solution. And notice that we have a way to get from grams of solution to grams of lead. We're using that parts per billion conversion factor. 15 grams of lead in 10 to the ninth grams of solution. Now the problem is asking us to find mass in micrograms. This isn't a conversion factor I wanted you to memorize, so it's given to you in the problem. But I want grams to cancel out, and that will leave me with micrograms up top. So grams of solution cancel, grams of lead cancel, and I'm left with micrograms of lead, and that comes out to 6.8 micrograms of lead. Okay, let's do another one. So a 50-gram sample of industrial wastewater was determined to contain 0.48 milligrams of mercury. So we need to express this in parts per million and parts per billion. Okay, so let's write down, we're given 48 milligrams of mercury, and it's in a 50-gram sample. So I'll just say sample here. That's the solution. Now, I can't just plug this into the parts per million formula here because I need both masses to be the same. So the first thing I'm going to do is convert that mass of mercury, I'm sorry, milligrams of mercury into grams of mercury. So there's 1,000 milligrams in 1 gram. And look at what I get. I get 9.6 times 10 to the negative 6 grams of mercury over 1 gram of solution. If I multiply that by 10 to the sixth, that will get me 9.6 parts per million. Now, if I want to express this as parts per billion, I'm going to do the same exact thing. So all of this is exactly the same. I get the same end result here. I just multiply by 10 to the ninth. And that's 9,600 parts per billion.